So last class, we introduced these comparison tests, and there were two different ones, but the way that every comparison test goes is there are a few steps in here. So the first thing is that you start off with some series, I'll call it AN. So you have some series, often it's sort of complicated. And what is a part of using these tests that does take a little bit of practice, or at least thinking about how it goes, is that you want to find a typically simpler series, say Bn, to compare it to. Then where things split up is there are two different comparison tests, and so you need to actually do this comparison. There's something you need to check or find which says the series I started with and the series that I'm comparing, that I'm come up with, they are comparable in some useful way. So this last part is do this comparison, which for the limit comparison test is with the second one we talked about. This said, find the limit of AN over BN, and we want to check that this isn't 0 or infinity. So that's the comparison that the limit comparison test says. That's what you want to see. The other one, the direct comparison test, you want to come up with an inequality, but which inequality you want depends on what this comparison series does. So the direct comparison test breaks into two cases. If Bn diverges, then we want that the Bn's are smaller than the AN's. So that's the useful comparison, because we can say, well, the Bn's already diverge, and these are even bigger. So those are going to diverge too. And then the other case is if the Bn actually converge, we want the opposite inequality, that the AN's are less than the BN's. So the BN's, if they already add up to a finite number and we get even smaller, then that's also going to add up to a finite number. And especially this case, this is because the A's and B's are always positive. So you could have a sort of dumb thing where the BN's converge, but the AN's are really, really negative. And so this only works when we have positive things, which says that these AN's here are greater than or equal to 0. And so they're kind of stuck in this range and they end up needing to converge. And then as always, there's this summary sentence at the end, which kind of wraps up what we want to say. But for these comparison tests, there are these two important parts. And while this finding a comparison series is you just pick one, we do want to spend some time thinking about how do you pick the right thing. here's an example where we'll end up using the limit comparison test. So let's look at the series from 0 to infinity, 2 to the n times n over 3n plus 1. And we want to figure out what this series does. So if we want to use a comparison test, we need to figure out what do we compare it to. And especially if you're doing the limit comparison test, you want to pick something so when you take or form the fraction and take the limit of that, you end up leveling off. You don't want to pick something way too big or way too small, because then that limit would be 0 over infinity. So you're looking at this and you're essentially thinking, what in here is most determining what happens to the terms of this sequence? And that's sort of a weird question, but in this case, what will happen is we can think of all the pieces in here, which are the ones that grow the fastest, because that either makes the fraction really big quickly or really small quickly if it's in the denominator. And in here, the thing which is having the biggest influence is this 2 to the n. If you were to graph these pieces, like 2 to the n as compared to like the line 3n plus 1, 2 to the n gets enormous really fast. And if n is 1,000,000, it's just so much bigger than the other pieces that you can essentially say these have almost no effect on how fast things are growing. So you pick out what in here is growing the fastest, and that's what we're going to use for a comparison series. So we'll say we'll compare this to the series, which is just 2 to the n. So this is a good choice because, well, it looks like our series. It looks like we've taken the big part of our series we started with, but also, does this thing converge or diverge? It diverges, and there are, I guess, 2 ways you could think about it. This is a geometric series. So it diverges since the absolute value of 2 is greater than 1. And for our geometric series, that's the threshold where we, I guess it was equals to, but whatever. That's the threshold where a geometric series diverge if your R is outside of 1 and -1, and it converges on the inside. You could also say, use the test for divergence here, which would also work because 2 to the n is going to infinity, definitely not going to 0. Either one of those works. But this is a simpler series, which takes the important part from our original series, and it's really easy to tell when it converges and diverges. So then we actually do the comparison. It's not enough to say, this is what I compare it to. You have to actually justify that it's a good thing to compare it to. So then we find the limit as n goes to infinity. An over bn means take the terms of one series and the term of the other series and form a fraction out of those. Whichever one goes on top and the bottom doesn't matter. Either way, you'll get a finite number, or if you get a finite number of one order, you'll get a finite number in the other order. So we get 2 to the n times n over 3n plus 1, all divided by 2 to the n. And now when we write this down, this is really, it's a sequence. We're not worrying about convergence tests. We're not worrying about series or anything. Just this is a sequence. What does it do? As a first step in most of these cases, you're going to have two or at least one fraction, often two fractions. And so you'll simplify those fractions and rearrange them a little bit. In this case, what we can do is say, taking this fraction and dividing it by something, that's equals to taking this 2 to the n and sticking it in the bottom of this fraction. So we can rewrite this as the 2 to the n times n on the top, but this 2 to the n can be put in the denominator here. And the thing to expect is that you'll either get, in this case, literal cancellation, or we'll see a little bit later, is you get like a rational function with the same powers, and that's something that has an asymptote. So in this case, the 2 to the n's, those are gone. And then we have n over 3n plus 1, the powers match, so we just take the numbers in front. That's the 1 and the 3, and so we get 30. So there's all the wrap-up step, but questions about executing this limit here. So then what we do, we get this number 1/3, and in the limit comparison test, there are a lot of or in all of these tests, there are different checks that you do. In geometric series, it's between 1 and -1. In the limit comparison test, all you care about is I didn't get 0, but the limit still exists. Yes.
We found 1/3. Like, since you kind of got rid of the part 1 at that point, you constant always get canceled out at that point?
So in this case, what's happening is you can either use you could use L'Hopital's rule, which gives you a 1 and a 3. You can also just say these powers match. And if those powers match, then the limit is the numbers in front of those biggest powers. Yeah, so we get this 1/3, and all we care about is that we got a finite number that isn't 0. And so then the limit comparison test says, so by the limit comparison test, the original series, or you can actually write down this series diverges. Diverges because we said our comparison series, it diverges, and this 1/3 says the two series you're looking at have the same behavior. So that's right. So the limit comparison test says if you get a finite number, whatever this simple series does, that's what the more complicated one does too. And it doesn't matter that this is less than 1 or anything like that. It's just saying the two series behave the same. Questions about this problem? So let's try another one. And let's look at the series going from 1 to infinity, n cubed plus 3n over n to the 4th plus 2 n to the 5th. So given this series, I guess what we can, when we're trying to decide what to do, I think one thing you might try is, we did some examples with these rational functions where we did a direct comparison test. So not like that example, but we did something where we said maybe 1 over n squared is greater than or equal to 1 over n squared plus 1. And this inequality could help us determine that the series 1 over n squared plus 1 converges. So in some cases, the direct comparison test, if you can see how adding this 1 makes it smaller, you can see the direct comparison, the actual inequality that works. This thing is just way too complicated to try that. So coming up with an actual inequality is tough. Maybe you could come up with some inequalities, but it's sort of a lot of work, and maybe you'll try to avoid that if possible. But this is actually a really good example of the limit comparison test, because sort of like we did here, if you're going to do the limit comparison test, it comes down to, what do you think this looks like if you look at the biggest parts of this series? And in this case, it's not, or what's different is it's all polynomials, so we don't have this distinction between the exponential function is just way bigger than these linear functions. But kind of like if we were just trying to find the limit of this, the question is really, well, the biggest powers on the top and bottom, that is essentially determining what happens. In the top, when n is really big, n cubed is just so much bigger than 3n that you can sort of throw away the 3n. And the same thing on the bottom. When n is really big, the n to the 5th is so much bigger than n to the 4th that the n to the 4th doesn't really contribute anything to what it looks like. So then what we can say is, well, let's compare it to the series where we do just actually forget about those smaller terms. So we can say, let's actually just take this n cubed, and even just this n to the 5th. You can throw in the 2 if you want, but it doesn't matter. Those are the big things that are really determining what the top and bottom separately are doing. And so we can say, let's compare this to the series that only has those two things on the top and bottom. So n cubed over n to the 5th, which here we can actually cancel all of the n's. We get n squared on the bottom, and that is a nice simple series that is really easy to tell what it does. This is one of the p series, and whether it converges or diverges just comes down to, is that number bigger than or less than or equal to 1? And 2 is bigger. So this thing, you can say this converges by the p-test, and what you're looking at is that the 2, the exponent, is bigger than 1. So that's the first step, figuring out what do you want to compare it to, and what does that comparison series do? And so we, picking out the biggest terms, get that there are 2 more n's in the denominator and 1 over n squared converted. But then you need to actually do the comparison to make sure that these two are comparable, which for the limit comparison test says we want to take the limit. Limit as n goes to infinity, this big thing, n cubed plus 3n over n to the 4th plus 2n to the 5th. And this whole thing is divided by this sequence, 1 over n squared. So we have 2 fractions. Take the bottom one, flip it, and multiply. And so we have n cubed plus 3n over n to the 4th plus 2n to the 5th. Flipping this gives us an n squared on the top, a 1 on the bottom, and then we multiply this through. And when we multiply this through, what you can see is this n squared is exactly the extra powers of n we need. So we're going to have a rational function with a horizontal asymptote. So multiplying this through, we get 2 extra n's in each of these terms. Limit as n goes to infinity, n to the 5th plus 3n cubed over n to the 4th plus 2n to the 5th. And with those extra 2's that we put in, now the biggest powers match. And that means this is a horizontal asymptote. There's the 1. In front of that, 1. There's the 2. And so this limit is 1/2. So for these rational functions, this is different combinations of powers, but this is what you would expect if your comparison turns out to be good. When you set up the fraction, flip it, and multiply it through, you end up with the same power. In contrast, what you might, like a not unreasonable thing to do would be in here. What if you just said this n to the 5th is the biggest power around? Maybe I'll compare it to just with an n to the 5th in the bottom. That's not a, it turns out to not work, but it's not like an unreasonable thing to do. So if you compared it to just 1 over n to the 5th, which would also converge by this kind of same reason here. The problem when you get to the limit here is you would divide by n to the 5th, you would put an n to the 5th up here, and you would get more n's on the top. So this would be limit as n goes to infinity. Well, I'll just write it, n cubed plus 3n over n to the 4th plus 2n to the 5th. And then there's this n to the 5th over 1. And if you multiply this through, you'll end up with n to the 8th over something with n to the 5th. And that's going to go to infinity. So if you don't take the right comparison test, the way that that is realized is when you take this limit, you get an infinity or you get 0. And that is really saying of the two things that you picked, one of them is much bigger than the other, so they don't sort of balance out in this way. So that's something to watch out for. It's as you're getting practice, you might just pick the wrong comparison series, which you're learning. It's okay to try things and them not work, but then you need to, one, how do you know that you ended up picking the wrong series? And that's, you get this infinity or zero. And then what are you supposed to do? So we go back and say this n to the fifth, we need more than just the biggest power around. We also want this biggest power on the top. And we want 1 over n squared, which is how they sort of cancel each other out. So that's not part of the solution, but is something worth thinking about. And then we get to finish this. So we said we have our series. We pick 1 over n squared, which converges, and this limit says that that is actually a good comparison. The two series, the one you started with and the one that you picked to compare it to, are going to have the same behavior because this isn't zero. So then the original series converges also by the limit comparison test. Questions about this problem? And so I think one place where the limit comparison test is really good, like something it's very well suited for, is series like this where it's all sorts of powers of n. In this case, integrating it would be really hard, so the integral test isn't going to work. There's too much stuff going on for a direct comparison, but the limit comparison test says just pick out the biggest powers of n, and that's what you want to compare it to. So even in some more more complex looking situations will be very similar to this. So let's see this. From 1 to infinity, and we'll take n over the square root of n cubed plus 4. So before I start talking about this, take 20 seconds or something and think about what would you compare this to? Especially given that I said a lot of things with just powers of n, you find that comparison series in sort of the same way. So what do we want to compare this to? So what do we want to compare it to? What do we think is a good series? And maybe to guide where you think a little bit more, what p series do we think is a good comparison test? So if I'm going to circle some stuff, what things should I circle to take into consideration when we try to come up with this comparison series here? Right, so definitely n to the third is just the biggest power around. So we're definitely going to need that. The n on the top, and like I did here, it's not enough to just take the biggest power when it's powers everywhere. You'll also want to look at the top. But that's not going to be everything. The thing to keep in, or the thing that is different in here, is that it's not just powers, there's that square root. And if you think of n being enormous, the plus 4 isn't going to do very much, but the square root is still going to be there. Whatever n is, you're going to cube it. The plus 4 doesn't really change the number if you're talking about billions of, or if n is a billion, but you are going to take the square root. So yeah. Also, let's do this. Let's also highlight the square root here. So what we're going to compare it to isn't just with the n and the n cubed, but it's also going to have that square root in the denominator. So n over the square root of n cubed. The square root of n cubed dealing with the exponents is n to the 3/2, and then combining the exponents from the n and the n to the 3/2 in the bottom is 1 over n to the 1/2. So that's what we'll end up comparing it to. And before we do the comparison, a quick check. It's a p-series. It doesn't converge this time because the p is on the other side of 1. So we'll compare it to this, which diverges by the p-test because 1/2 is less than or equal to 1. But then we can set up the comparison. Find the limit of these two, of the fraction made up of these two series. The limit as n goes to infinity. Let's say 1 over the square root of n. This one, for the algebra I'm going to do, I'll like having the square root, but you could use n to the 1/2. That's the same thing. Over this big gross fraction, n over the square root of n cubed plus 4. The move, which is always there, flip things around to get a single fraction rather than a fraction made of other fractions. So flip this and multiply. What does that end up being? So we get 1 over the square root of n times the square root of n cubed plus 4 over n.
Does it matter if you divide the original one by the comparison one, or because in that one you divided the one you start off with by your comparison, and in that one you divide your comparison by what you started off with?
Right, so that won't end up mattering. If, I guess in this case, if you flipped the order, then all the fractions would get flipped. And the end result would be the 2 would be on the top and the 1 would be on the bottom. So you get 2 rather than a half. But if what we're checking is, did you get a finite number that isn't 0, then even if you take its reciprocal, that's another finite number that isn't 0. Right, so it doesn't matter. I think this is what I had written down in my notes, but you could do it the other way and it would still work. All right, so then we can combine this together. This is a little more complicated, so we have to think about what's going to happen. And so we can combine these exponents. This is n to the 3/2 on the bottom. And the 3/2. And the way that we can write this, which I think makes it the most clear what is happening without trying to stretch too far from other kinds of limits we've seen, is n to the 3/2. That's this thing. That's the square root of n cubed. And if we put that square root in, we have access to some more algebra, which I think makes how we find this limit a little bit clearer. Because we can rewrite this as our square root of n cubed plus 4 all over the square root of n cubed. And let me and set up like this. A root algebra rule is if you're taking the square root of two pieces of a fraction, you can use a single square root and just have the fraction on the inside. So looping around here, we can rewrite that as a big square root over n cubed plus 4 over n cubed. And written like that, the way that we can analyze it is limits can be brought inside square roots. And if we take the limit of this inside, this is a rational function, the powers match. So we have n cubed and n cubed. So this is the square root. When we take the limit of the inside, we get 1, which is 1. And for the limit comparison test, there's 1 is still okay. It's in the geometric series, it's this cutoff we have to watch out for. Here it's just another number. And then we get to wrap this up. We got a finite number. That means we do have a good comparison. The two series do the same thing. Our simple series diverges. So by the limit comparison test, the original series diverges. Questions about, I guess, any of these problems as you've had some more time to let them marinate a little bit? But I guess specifically this.
On the last one, you got 1/2 for the solving the thing, right?
Yeah.
How come that converges?
So in the limit comparison test, the number you get, the actual value doesn't matter. What you're checking is, did you get a number which is not 0 and not infinity, or doesn't it exist? The reason for that is that when you're forming this limit, what you're saying is how many times bigger is this series than this series. And if whether it's twice as big or half as big, if you have something that converges, then twice as big is still converging, half as big is still converging. And for diverging, if you're half as big as something that diverges, well, the diverging thing is going infinite, you're still going to go infinite too. So in this case, we don't really care what number we get, a half, 1, 6. As long as it's not 0 or infinity, they're comparable to each other in that there's a multiple, or that basically one is a finite number of times bigger than the other one. And so that's why we can say they do the same thing.
Yeah, but I was saying you got one this time and 1/2 last time, and they both don't equal 0, and one diverges and one converges.
Right. So, okay. So then the other thing is you get this number, and the number on its own isn't going to tell you what happens. The number says that the two series you have are comparable and do the same thing. So when you get this 1, what that says is, right here, I found out that my comparison series diverges. This is going to do the same thing. So what you would like to say, or the kind of less careful version of the limit comparison test, is this series is basically the same as this series, so they should do the same thing. And since this one diverges, this one also diverges.
Okay.
The limit comparison test fills that in by saying, well, what do you mean basically the same? And one way that lets you come to that conclusion is if this limit is a finite number.
Okay.
So one, I don't know, I guess restriction for these comparison series is that things always have to be finite, or sorry, not finite. The series always have to be positive. You can't have negative numbers. In particular, you can't have alternating series. So for instance, you can say that comparison tests don't help with series that look like this, -1 to the n over n squared. In which case, the comparison thought is, well, this looks like just 1 over n squared. Do they do the same thing? We can't use the comparison tests because those need your series to be positive, and this has half its terms negative. So we need something else. And actually, for alternating series, there is a very narrowly applicable but super easy test for these. So what I'll mean by alternating series is more or less series that look like this. So these are series where your series has an alternating part and Bn where the Bn's are greater than or equal to 0. So by an alternating series, I mean there's some positive sequence, but you're letting it alternate. And so this would be something like negative B1 plus B2 minus B3 plus B4, and then so on. Or it could start in the other way. It could start with positive B1 minus B2 plus B3, and then so on. So whether you start with a positive or negative doesn't really matter, but if it keeps flipping, and because the B's are positive, it really does change from positive to negative to positive to negative. And so in observation, which is not deep, but worth pointing out, so the absolute value of the ANs is the BNs. You either get rid of the negative sign or it's already positive and nothing happens. So for alternating series, there is a convergence test specifically designed for them, and it's really well named. This is called the alternating series test. And so what this looks like is if you have an alternating series, so we have the alternating part minus 1 to the n, and then the positive part b to the n, or bn. If this has two properties, first, the limit of the b's is 0. One thing. Second, not only are the b's going to 0, but the bn are decreasing. So if you're given a series, the alternating series test says, forget about the alternating part. We're not really going to do anything with that. Just look at the main part of the sequence, and is it decreasing, and does it converge to 0? If it has those two properties, then the series converges. And that's all there is. So it's super easy to use. Two pretty easy things to check. The trade-off is that it only applies to alternating things. And it really has to be alternating. It can't be things that are sometimes positive and sometimes negative. It really needs to have this alternating part highlighted there.
How we doing, Ellie?
So for instance, well, we take that series that I had written out there from 1 to infinity of minus 1 to the n over n squared. So it is alternating, so we can use the alternating series test. And we can, for emphasis, say that the bn's are 1 over n squared. First thing, what is the limit of this? Well, the bottom's going to infinity. This thing is 0. Second, n squared is increasing. So 1 over n squared is decreasing. Done. And then that's the whole thing. So by the alternating series test, the series converges. we'll talk some more about this, but really there's not a lot more to say. I guess the biggest thing that we'll focus on, which is sort of a question that we haven't really talked about yet, is does it matter that this alternated or this converged even if you didn't have the -1 to the end? So 1 over n squared converges. What does the alternating part do? Like, how is this really different? Well, this is where we'll start on Friday. All right, so I will see you all on Friday.